All right, so we have gone ahead and finished what I like to call differentiation calculus, where we talked all about derivatives of a single variable function and some applications of those derivatives. Now we can start approaching into the second major part of calculus. You might call this part maybe unit 2 of like 4, something depending on how you split up the entire cal sequence. We're going to talk about antiderivatives, or in other words, we're going to very quickly call this integral calculus. We're going to talk about what is integration in terms of math and stuff like that. We might get to some applications by the end of the semester, but we'll see how far we get. But we'll talk about integration. All right, so I already gave y'all a preview of this in the last class, but to recap, well, before that, sorry, let's talk about what is an antiderivative. So a function, I'm going to use capital F, is an antiderivative of little f if the derivative of big F is equal to little f of x. For all x's in my interval, per se. So we are introduced to the idea of an antiderivative. To clarify, so far what we've been doing is saying we get f and then we get the derivative f prime. An antiderivative says that instead of going, in a sense, down on my ladder, I can go up onto my ladder. So taking the derivative takes me down in a sense. And we're going to learn about this thing called integration, which is going in the reverse direction almost. So the derivative of f, big F, is little f. The derivative of little f, we have f prime. Or if you want, you can put this in terms of first derivative of big F and then second derivative of big F. So antiderivatives. Yes, quite literally equal. So if big F is the antiderivative of little f, that means if I take the derivative of this, which is f prime, I get little f. And then I can take the derivative again, I get f double prime. So yes, I mean very literally equal in this case.
Does this mean it's maybe something like a trick question on a test where it's like, give me the prime of big F when f of x equals something?
I probably won't have a question like that. Generally, this big F, I'm only introducing it for whenever we first have our idea of the antiderivative. We're very quickly going to move on from this notation in a little while. This is just for introducing it. Another way that you could word this is that, again, if I have f and f prime, that means little f is an antiderivative of f prime by the same definition. So again, instead of going down, we're out talking about going back up. Usually we had a function and I got the derivative. But what if I had the derivative and I wanted what could be the original function? There's one little key English thing here that I want to note. One thing I want y'all to notice is in this definition, note that I used the phrase big F is an antiderivative instead of saying it is the antiderivative. So we're going to see, what does that mean? Why did I use an as it is one of the antiderivatives instead of the antiderivative? And y'all are going to be able to actually see this in just a moment. So we have the definition of an antiderivative. And also the word antiderivative, we're very quickly going to move on from that and actually use a different term. Antiderivative is just to largely to introduce people to how it's the idea of it. All right, so let's move on from here. So we've already done this last time. If I have the function x to the n power, we know the derivative through power rule is bring down the power, reduce the power by 1. By power rule, multiply by the power, subtract 1 from the power. This is what we're used to. That's me going down. And if I want to go back up from the derivative to this original function, we would do the opposite operation in reverse order. So opposite of subtracting 1 from the power would be, well, adding 1 to the power and then dividing by the new power. And that's how we would sort of go back up our ladder of differentiation. So what I just did here, well, sorry, I'm timing this, my timing's all off today. Now I can finally talk about that, why I said an antiderivative instead of the antiderivative. So let's say I have an antiderivative big F of little f. Then as it turns out, all antiderivatives of little f have the form big F plus a constant c. Where c is an arbitrary constant. It's just a placeholder for some constant that we're not too sure of. It could be any value, actually. It's arbitrary. So let's look at this. Let's say I have a function f of x is equal to 3x squared. And let's say I want the antiderivative of that function, an antiderivative of that function. So I want big F of x. So the way I'm going to start wording this out is the derivative of what function gives me 3x squared. We can do this 2 ways. You can think, all right, let's think of all the functions that the derivative would give me 3x squared. Or I can do that operation, that order that I did on the previous slide, the opposite of the power rule. So looking at this, would y'all agree that if I write x cubed here, is it true that the derivative of x cubed gives me 3x squared? Is that true? Yeah, for sure. So what is this theorem saying? I have one antiderivative right here. I claim this theorem is going to claim actually all of my antiderivatives will look like x cubed plus a number. Why is that still true, even if I add a number?
Because constants are 0.
Yeah, the derivative of a constant is 0. So no matter what this number is, the derivative of this will be 0. So if I started off right here, I didn't know if I had x cubed plus 4 or just a plain x cubed. I knew I had an x cubed, but I didn't know if there was a constant involved in there. Because the derivative of a constant, we get 0. So that tells me that actually all of my antiderivatives of 3x squared should look like x cubed plus a number. Again, right now we don't care what that number is. I just know it could be plus a number, or it could be plus 0 also. Yeah, it could be by itself x cubed, or be x cubed plus 5, x cubed minus 28, x cubed plus pi, whatever. So actually what I did here, now instead of calling this an antiderivative x cubed, I call it the family of antiderivatives because we have an infinite number of options. Because C can be whatever your favorite number is. All right, so let's move from here now. X squared. This is just me reiterating what we had earlier, plus C. So here I have just an example with x squared. I think we can agree if I took the derivative of this, then I would get this function. All of these still have the form x squared plus or minus a number. So all of these are examples of antiderivatives of this function. So these are all part of the same family, we'll say. All right, so now let's see if I timed this correctly now. Going here, this is reiterating our derivative is the same. All right, so let's go ahead and look at our first example about the antiderivatives. Determine the antiderivative family of the following functions. So in this first one, I have f of x is equal to 11x to the 21st power minus 9x to the 17th power. Let's figure out what capital F of. So if I want to find the antiderivative of this, earlier we talked about how we would go in the reverse direction of the power rule. What was that order again? What was the opposite of the power rule? Like, did I add, subtract, multiply, divide? Yeah, add 1 to the power, divide by the new power. So that's what we're going to try here. So what's 21 plus 1? 22. And then, so I have 11x to the 22nd power. I add it 1 to the power. Divide by the new power, 22. Over 22, I guess. What's the next part I can write here? Well, I have minus 9x to, what's the new power? 18. And then I divide by 18. So that's me doing sort of the opposite of my power rule for differentiation. And what was that? Yeah, you can put it on the side. It means the same thing. So if I just want to clean this up a little bit, just for the sake of cleaning it up, 11 over 22, yeah, we get 1/2. So if you want to write on the side, for example, you could write this. Or you can write x to the 22nd over 2. They mean the same thing. Minus 9 over 18, we also get 1/2. This is me cleaning it up. And I'm going to throw on one extra thing. I'm going to go ahead and put plus C. Because I know all of the antiderivatives of this original function look like this, possibly plus or minus a number. So we have part A. We're sort of using this rule. We haven't really given it a name yet, but it looks like the opposite of the power rule for differentiation. Any questions about how I got this antiderivative family here? Let's go ahead and try it for part B. Part B, I have h of x is equal to 12 over the square root of x plus 12 square roots of x. What's one thing that we always like doing with square roots whenever we did derivatives? Yeah, we like converting those radicals into fraction exponents. So before I even try to take the antiderivative, let me go ahead and rewrite this. So first off, would we agree that 12 over the square root of x, that's the same thing as 12 times x to the negative 1/2 power. The 1/2 coming from the square root, negative because it was originally on the bottom. How could I rewrite the second? Yeah, 12x to the 1/2. Again, 1/2 because it was a square root originally. It's still a positive 1/2 because it was on the top originally anyway. So I haven't done the antiderivative. All I've done was just rewrite this for my own purposes. So let's go ahead and try to get the antiderivative of this one right here. So I'm going to apply that same property. Let's add 1 to the power. What's negative 1/2 plus 1? Yeah, we get 1/2. So I have 12x to the 1/2 divided by 1/2. So that's add 1 to the power, divide by the new power. We're going to clean that up in just a moment. Now we do the same thing for the other part. 12x to the 1/2 plus 1, we get 3 over 2 divided by 3/2. And then now I just want to clean up because we don't like having fractions inside of a fraction. How do I deal with dividing by 1/2, for example? Yeah, dividing by a fraction is equivalent to multiplying by its reciprocal, or you may have heard the term keep, flip, change. I keep the whole top expression, I flip my fraction, and then multiply by it. So in this case, I get 12 times 2 over 1, or 24x to the 1/2. Plus, let's see what happens whenever I flip 3 over 2. That's 12 times 2/3. What does that give me? 12 times 2/3, I believe that gives me 8. 8x to the 3/2 power. Am I forgetting something here that I did in the previous problem? Plus c. Because we don't know which antiderivative we're talking about. I have to put that plus c. And I want to take note of something else as well. You can always check your answer. If I did this correctly, when I take the derivative of my answer, I should end up at my original expression. So derivative of this, I should end up here. So let's see real quick. Derivative, bring down the 1/2, 24 times 1/2. I get 12, 1/2 minus 1. Yeah, I get negative 1/2. Bring down the power over here. 3 over 2 times 8. I get 24 over 2, or 12. 3/2 minus 1. I get 1/2. Check. Derivative of a number, I get 0. So everything does appear to match up for us. So again, when we're finding the antiderivatives, we can actually check our answer to ensure that it's all correct. And this is also one of the reasons why I said before, it's really important that we know our derivative rules because they allow us to check our answers in integral calculus. Go ahead and see if you can do part C. See if you can find capital K of t, the antiderivative of little k. And I'll go ahead and write the answer on here if you would like to check your answer. I guess I'll write out the entire thing. 9/4 t to the 4/3 plus get 3t to the 2/3 7t plus c. And let me just double check that real quick. That's good. Check. 2/3, 2. So yeah, go ahead and see if you can figure this one out, and you can compare it to what I have as the final solution. 4/3. There we go. So this one's just generally repeating what we did in the previous example. But this time I gave you our variables with the fraction exponents ahead of time. One thing to be careful about is that it is very easy to accidentally mess up your arithmetic here. Like 3 divided by 4/3. If you're trying to go really fast, it could be easy to mess it up. I'm sure that there'll be at least one moment through the semester where I'll mess up a quick calculation. But we have 9/4 t to the 4/3 power plus 3t to the 2/3 power plus 7t plus c. Do we have any questions about any of these parts of example 1 before I move on? All right, so I'll go ahead and clear the screen here. Now let's go ahead and use our more formal terminology now, or common terminology. If I ever ask you to find the antiderivatives of a function, it's actually more common, especially whenever you move on to Cal 2, that we say that we integrate the function. Or to be more exact, to say that we evaluate the definite integral. So if you ever hear me say, let's integrate the function, then I'm just saying, give me the antiderivative. Hence leading to the section of this, the title of the section, integration of a function. If you're reading this, you might also notice the second phrase, evaluating the indefinite integral. That's going to make a little bit more sense in the next coming sections for the next couple of weeks. Actually, I think that y'all can make a little bit of a connection about why we call it an indefinite integral. So, not necessarily that we can keep going. The existence of an indefinite integral, you can probably say that it implies the existence of a definite integral. That can be partially related to it, but it's going to be something that it's going to have to do with our upper and lower bounds. And also it's going to be related to the application of the integral, about what is a definite integral. So just giving anyone any time to copy this down. It's really just terminology, not really anything. In other words, from this point on, you're probably going to hear me start saying, let's integrate the function or find the integral, instead of saying find the antiderivative. All right, so here's the notation we use to say integrate the function. It looks like sort of like an S that's been stretched out. So I think I have these labeled as well if I did it. Nope. This is our function that we are integrating. Sometimes you'll see a book called this, the function that we are integrating, called the integrand or integrand. I don't know if the D is a hard D or not. So if you ever see this integral symbol with the dx, it's telling me find the antiderivative of this function. This dx also tells me what variable we are in respect to. So if it was dx, that means we're integrating in respect to x. If it was dy, we are integrating in respect to y. In other words, it just says what variable I should be using here. For the most part, we'll be working with dx, but sometimes we'll play around with like t or theta or other commonly used variables. One thing that I always like to say for students also is that usually this integral symbol and the dx, they're a package deal. These are usually going to be almost always seen together. Together. I didn't have a good word for this. So in other words, you're not just going to see the integral symbol. Like you won't see something like this. It has to be the integral symbol with a d something. So just some notation here and there. So actually, instead of the instruction saying, find me the antiderivative, a lot of times you're going to end up saying evaluate or integrate, and it'll just have something like this right here. All right, so now that we're familiar with the notation of the integral, let's go ahead and point out some things here and there. Our theorem. If I take the integral of x to a power, then this is equal to me adding 1 to the power and dividing by the new power for some constant number p. But there is one p-value that doesn't work here. -1. Why would -1 not work out? Yeah, because -1 plus 1, I would get 0. And then that would mean I'm dividing by 0. So if I had this animation properly, oops, it does not show up. Not equal to 1. -1, sorry. Not equal to -1. So if you ever have x to a power besides to -1 power, you can actually go ahead and get the integral. Does anyone have a guess what is the name of this integral rule? What is this the opposite of? This looks like the exact opposite of the power rule. Yeah, so before we had the power rule. We didn't really give it a name beyond that, but really it was a power rule for differentiation. This one could be called the power rule for integration. All right, so some things that result from here. I know if I took the derivative of a sum, that was equal to the sum of the derivatives, which was a fancy way of me saying, if I had a bunch of things added together, I could take the derivative of each one down the line. Well, as it turns out, I can actually do the same thing for integration. That is, if I take the integral of a sum or a difference, that's the same thing as taking the integral of each one individually. And this is similar to the derivative rule. We're rarely going to, I guess not necessarily rarely, but it's not often that we'll be seeing us writing this out explicitly. Because we'll just say, let's take the integral down the line each time. Let's think about another derivative rule. For derivative rules, we know that coefficients just kind of went along for the entire process. The same thing happens for integrals. So again, if I time this correctly, and if I have a constant times a function, I can factor out the constant. And I want to make sure that this is not equal to -1. So we could have all these fancy names for each of these. The top one, often you're going to hear me call it power rule for integration. The second one, if I want to give it a fancy name, it's like linearity of an integral, which again is a fancy way of saying I can take the integral of each part of my sum or difference. And actually, y'all already did the second rule already in the previous example. Remember I said find the antiderivative? We did the antiderivative of the first one, and then the second one, and then the third one. So really, y'all have already seen this without really knowing it was this rule. All right, so we have this rule, this notation. Let's go ahead, and I claim that y'all can do each of these somehow. Evaluate the following indefinite integrals. We're kind of glazing over the word indefinite. All will be revealed in the next coming weeks about why it's indefinite. All right, so for part A, I have the integral of 8 cosecant squared of x dx. What is this equal to? Remember, whenever I'm asking for an integral, I'm saying the derivative of what function gives me this expression right here. So the 8 I can carry along for the process. This is just for notes. Usually I wouldn't write it this way, but I could write this. I could factor out the 8 from the front. And then 8 is already there. So do I know about a function where if I take the derivative, I get cosecant squared of x? Is it tangent? What's the derivative of tangent? Derivative of tangent is secant squared. Is it just a plain cotangent? What's the derivative of cotangent? Yeah, derivative of cotangent of x is negative cosecant squared of x. Therefore, if I want to get negative cotangent of x. And really, the only thing I can do from here to clean it up is multiply 8 and -1 to give me -8 cotangent of x. Am I done here? Plus c. It may seem a little bit arbitrary, but it's important that we put the plus c anytime I do an indefinite integral. In fact, to emphasize the importance of this plus c, once we get to that final exam later on, every time that you forget to put plus c, that is -1 point for each time you miss it. So please make sure that you include plus c whenever you do an indefinite integral. The unfortunate story I have about people forgetting plus c is one time I gave an integral exam where there were 20 integrals, and this person forgot to put plus c for all 20 of them. But we have part A complete, and again, we can check our answer. Derivative of cotangent of x is negative cosecant squared of x times negative 8. I get this original expression. All right, so what about part B? Does anyone have an idea what the answer for part B might be? To help start y'all off, let's take out that 4. I would agree that this is the same thing as 4 times the integral of 1 over r squared plus 1 dr. So do I know of a function where the derivative is 1 over r squared plus 1? The derivative of some function giving me 1 over r squared plus 1.
I'm gonna take a while with the same -2 r to -1 power.
What was that?
-2 r to -1 power.
Not -2r to the -1 power, because then where would the plus 1 come into play?
Plus 1 had -1 too.
No, well, we know that it wouldn't exactly turn out that way because that would mean that r and 1 should be on separate parts, not together. Yeah, arctangent. You can say arctangent, tangent inverse, whatever way you like to write it. I'm going to go ahead and write it as 4 tangent inverse of r plus c. We know the derivative of tangent inverse is 1 over x squared plus 1. Again, another reason why I said all of those derivative rules that we learned through the entire semester, they get used again. But now you're thinking in the reverse direction. So far, any questions on parts A and B? Now let's look at part C. I'm going to clear the screen so that I have space for it. And we're going to break it down step by step for convenience. So looking at this, if I did want to write out every single step here, I know the integral of a sum is the sum of my integrals. In other words, I can split this apart if I wanted to and write this as integral of 4 secant x tangent x dx plus the integral of 1 over 2x dx. So I'm allowed to do this. Would I usually write this? Maybe not, but for the sake of notes, I'm going to go ahead and write it down like this. So let's focus on the one on the left. Does anyone have an idea what can I do to try to figure out what this integral is equal to? Yeah, so the 4, I can keep it along for the ride. And now I got to ask, what is the integral of secant x tangent x? Or in other words, the derivative of what function gives me secant x tangent x? Derivative of cosecant? Let's see, we know the derivative of cosecant should be negative cosecant x cotangent x. What was that? Not cosine. Derivative of cosine is negative sine. Derivative of secant, yeah. Derivative of secant x gives me secant x tangent x. Secant of x. That covers this first one. What about this second one? What can I even do for this other one?
We're gonna make it
Well, we can't make it x squared because it's not x squared on the bottom. Not that's going to come out as 0. Remember in my rule earlier, we could use that power rule for integration, except when the power is -1. Let me write this down and see if this jogs your memory. Would you agree that I can take out a 1/2 from here? Okay. I can do this. Do I recognize that integral of 1 over x dx? Is there a function where if I take the derivative, I get 1 over x? Not arctangent, but it's actually the natural log function. Remember, derivative of the natural log of the absolute value of x, we get 1 over x. Therefore, I get 4 secant of x plus 1/2 natural log of the absolute value of x, like so. All right, do we accept this answer? Correct, we need a plus c. Do not forget the c, otherwise you only gave me one antiderivative. You did not give me all the antiderivatives. Another way that I could word this, if you forgot the plus c, you forgot almost all of the solutions, and you only gave me 1 out of infinitely many. So you basically gave me 0, because 1 over infinity, roughly speaking, we would get 0, because we know that from our limits. And again, we can double check our answer. Derivative of 4 secant. We get 4 secant x tangent x. Derivative of 1/2 natural log of x, we get 1/2 1 over x. So I know that this answer should be correct. One little side question I want to ask here is that I said that every time we do the integral, we put plus c, right? Can someone tell me why did I not put plus c here and then another plus c? Why do I not have 2 plus 2c? Well, yeah, we have done that. But what's stopping me from doing it earlier after I integrate each one individually? Yeah, but why not? Why not 2c? Why not 3c? So remember, c is an arbitrary number. 3 times an arbitrary number is just a larger arbitrary number. So in other words, yeah, I could put plus c each time and then put plus 2c, but 2 times a constant is just another constant. And why bother putting 2c, 3c whenever I can say c for any number? All right, so let me just take a quick look and see what's on this next slide. I don't think we'll continue from here. Okay, perfect. Place to stop. So this is where I'm going to stop today. I'm on our introduction to integration. So let me end this here.